In artificial intelligence, the diffusion models refer to a class of generative models that can create high quality samples of data, such as images, audio, or text. The process involves starting with a distribution of random noise and gradually transforming it into a sample of the target distribution, or, for example, a set of realistic images, through a process that reverses diffusion. Diffusion models are inspired by the physical process of diffusion, where particles move from areas of high concentration to the areas of low concentration until they reach equilibrium. In the context of AI, the diffusion process is simulated in two main phases. The first phase is called as forward process, or the process where we add noise. This process incrementally adds noise to the data over a series of steps, gradually transforming the data from the original form into pure noise. This is done in controlled manner, often using a Gaussian noise model, and the process is typically Markovian, meaning each step only depends on the previous state. In the second phase, which is called as a reverse process or generating data, that is where the generative aspect comes into play. The model learns to reverse the noise addition process, starting from the random noise and step by step reducing the noise to generate a sample that resembles the original data distribution. The reverse process is learned through training on a dataset where the model is trained to predict the original data from the noised version. In the research paper, which you can see on your screen, Meta's Diffusion World Model, or DWM, introduces a groundbreaking approach to predict multi-step future states and rewards concurrently, and it has already outperformed traditional one-step dynamics model by a substantial 44%. This enhancement facilitates long horizon predictions efficiently in a single forward pass. If you go through their paper, they have come up with this two-staged approach where world model training and second one is offline policy training. The problem which they are trying to solve is that the traditional reinforcement learning models face challenges with compounding errors during multi-step predictions, limiting their effectiveness for long-term planning. This issue hampers the accuracy and reliability of predictions. This is where this model helps a lot, as it works by integrating conditional diffusion models with offline reinforcement learning to generate future trajectories. This model bypasses the need for recursive queries, using generative modeling for value estimation and enabling synthetic data used in offline Q learning. The approach combines robust long horizon simulation capabilities with state of the performance achievements. I don't have the code as of now because they haven't released it, but if you read through this paper, it seems that that will be released soon. And as soon as I got my hands on this paper, I will show you as how it works in the real world in action. I will drop the link to this paper in video's description too, so have it a go, and as it's quite nicely written. That's it. I hope that you enjoyed it. If you like the content, please consider subscribing to the channel, and if you're already subscribed, please consider sharing it among your network, as it helps. Thanks for watching.